This section is on the goodness of fit test. Perform a goodness of fit test. Some data are counting categories rather than measurements. In this case, we would like to test whether the proportions or counts in each category are what we expected. These methods examine all the categories and all the proportions or counts in a single test statistic. Okay, so what are we talking about here? For example, we roll a die 600 times, right? The question is, does this set of counts differ significantly from what is expected? What do we expect to occur? Well, if this is a fair die, and there's 6 sides to a die, and we chose that number 600 times just to make the numbers very easy. If we roll it 600 times, well, each side should show up 1/6 of the time. And that would make it that each side should show up exactly 100 times. So that's what we would expect to happen. Will that happen all the time? Probably not, right? Some sides might come up 90 times, another side might come up 110 times, but the expected counts for each side should be 100 for each because it's a fair die. In another example, what if the outcomes or categories don't all have the same probability of occurring? For example, a manufacturer of M&Ms claims that the distribution of plain M&M candies in a bag is 13% brown, 14% yellow, 13% red, 20% orange, 24% blue, and 16% green. So that should all add up to 100%. You see how each category or outcome has a different probability of occurring if we were to just randomly choose one at random. So if we buy a bag of M&Ms, does our actual count differ significantly from what we expect it to be? Okay, so these are the types of questions that we can actually examine, right? If there's a claim that it should be expected to be this way, right, in these types of distributions, and we actually go out and sample on our own to test if the distribution in our sample matches what is expected. So you can see how this can lead to some sort of hypothesis testing, right? Testing a claim on the distribution of the population to be. So a goodness of fit test is a procedure used in inferential statistics to determine whether a frequency distribution follows a specific distribution. That is, it compares observed counts, again, from our sample, that's what we observe, and the claim expected counts. Expected is from the null hypothesis, right? We expect it to be like this. This is the status quo expected counts. So again, when dealing with these hypothesis test types of problems, we always have some sort of status quo statement, and we have to get some data so that we can compare what is expected and what we actually observe. Continuing, it is used to test a claim regarding the distribution of a variable based on a single population. So in this section, we're dealing with a single population. If you wish to compare 2 or more populations, you must use tests for independence homogeneity, which are going to be covered in the next section. A few remarks here. Goodness of fit tests apply to experiments that consist of a series of n independent trials. So in our example of the die, let's think of our die example. Now in our case, this would lead to the number of trials. Well, we roll that die, if you look back up there, 600 times. Let me just try to get that in the same window here. Yeah. N equals 600 times that we roll it. Each trial has k that is greater than 3 different possible outcomes, so 3 or more different categories. So in each trial, unlike that binomial, remember when the binomial was just 2 outcomes? In this case, well, how many outcomes are in a single trial? Well, we are keeping track of each side in this case, so there are 6 sides. So k would be 6 sides in our die example. And P1, P2, ... up to Pk, so in our case P6, are the probabilities of the k outcomes, so the 6 outcomes, where 1 pi is for each possible outcome category. So what they mean by that in our example of a die being rolled 600 times is the probability of each side occurring. So we do know that for 1 to occur, that probability is 1 in 6. 2 occurs, that's also 1 in 6. All the way up to Pk, which in our case is the 6th side, that's also 1 in 6. In this case, yeah, they're all the same, but for like the M&M example above, these values would be, I guess you can call like brown being P1, that would be 13%, yellow being 14%, and so forth. Okay, so that's just an example there. We'll do some more. Okay, now what are the expected counts? Well, there's two different situations. Okay, in general, this first equation applies. Okay, the expected counts for each possible outcome are given by this equation. Mostly paying attention to n times p. Okay, and once we do an example, that'll make more sense with this, what we're saying here. Now, if each possible outcome are the same, for example, like the die, your fair die, then the expected outcome would be n over k. So, for example, the expected counts here would be n. In our example was 600, and k was the number of outcomes, 6 sides, and we get 100. That's how many outcomes we expect for each one of the sides. 100, 100, 100, 100, 100, 100 for each side. And I do want to add in one extra piece here that I didn't put into the notes. The sum of all the expected counts should always add up to the total number of observations. Again, right now it just seems a little abstract, but once we do an example, it'll make more sense. Okay, so we're going to get into the 6 steps of doing a hypothesis test. And of course, there's always conditions, initial conditions that we need to meet. Now, if a claim is made regarding the distribution, we can use the following steps to test a claim that provided that the samples are obtained using simple random sampling. That's a common requirement there. The next two are all expected frequencies are greater than or equal to 1. Okay. No more than 20% of the expected frequencies are less than 5. Now, these you won't know until you start doing the problem. In the real world, if those last two requirements are not satisfied, one option would be to combine two of the low frequency categories into a single category. Okay, so for example, let's say we're thinking about the M&M example, right? Let's say we don't get enough counts that are greater than 5. Then let's say like red and yellow were like the lowest count ones. We might want to combine them as a single category, like red and yellow as a single category instead of them being separate. That's what they mean by that. But I choose problems that you don't have to actually go about doing that. Okay, they're pretty straightforward. But in practice, that's what you would actually do. All right, step 1. Determine the null and alternative hypothesis. Let the hypothesis be constructed by. Okay, so in words, the null hypothesis is that the random variable follows a certain claim distribution. Okay, and the way I denote that just in symbols is that you literally have to list out all the proportions for each category. Okay. Now, if they're all the same, then you can set them all equal to each other and then just have them all ultimately equal to one value. And we'll do an example showing that. And the alternative is that all you have to do, the only thing necessary in order to dismiss the null hypothesis is that if we have enough evidence that one of these proportions is different than it's expected to be. You really just need to write at least one of the proportions is different than it's expected to be. It's just implied there. Okay, step 2, same step 2 as before, significance level. Your test statistic. You know, this test stat is a little weird looking, but it's actually not too bad. We have observed counts, so you're going to have a list of observed values. And we're going to have to calculate the expected counts. Okay, and that's done from the same calculation from the previous page. All right. For each of the K categories. And then we're going to compute the test statistic by hand. You can do it like this. Okay. You might need to use a calculator for this. And I'll show you how to do this. And to find the p-value for this, you'll need to use a function called GOF test in your calculator. Now, not all calculators have this function. If you have a TI-84 and above, you will have this calculator. But for those of you who have a TI-83 plus, I'll show you the workaround on this. And the degrees of freedom here are the categories minus 1. So if we have the 6-sided die, the number of categories is 6. 6 minus 1 is 5. So 5 degrees of freedom. Step 4, we're going to be drawing a graph here. The nice thing about this is these are always going to be right tail tests, which is really nice to deal with. Okay, always going to be right-tailed test. We have a 0 here. The test stat is right there at that partition. The p-value would be the area to the right of that test stat. It is a chi-squared distribution because the test stat is a chi-squared. Okay, so finding the test stat and p-value using a calculator. All right, so there's a couple different ways. Okay. First, enter your observed count in L2 and expected values in L1. Now this order, the specific order of observed in L2 and expected values in L1 is only required for the Math 200A program if you actually happen to have that in your calculator. Okay, this is an external program that you would have to either get from me. I don't know if you can find it online, but then again, you would have to have a cable to upload it to your calculator. But nonetheless, if you have a TI-84, you don't actually have to follow those instructions at all. Your calculator already has this function. Now, again, you have the liberty of putting it in L2 and L1 for either observed counts or expected counts. You really have the liberty here. You just have to make sure that you correctly identify it. Each list and you remember which list the observed and the expected are in. Okay. But if you have that Math 200A program, you actually have to do in their specific order because that's the way that program was created, that they actually specifically want a certain order. Now, for those of you with a TI-83, now if you don't have that Math 200A and you are using a TI-83 Plus, okay, so what you're going to do is calculate the p-value using chi-squared CDF. It's not too hard. We've actually used this function before. This is found in the distributions menu in your calculator. From the graph, the lower would be your test stat, right? That's your lower value. And then it goes all the way to E99, right? Is infinity. And your degrees of freedom would be k minus 1. So the hardest part is just coming up with the test stat here, really. Because that's what your lower value would be. Okay. And I'll go into detail on how we calculate that. There's a couple ways to do it. You can either do it by hand, you can put a list into a calculator. I'll show you how to do that. And of course, step 5, compare the p-value with alpha. We're making our decision to either reject the null hypothesis or fail to reject the null hypothesis. And of course, in step 6, we're going to answer the question in the context of the problem. We'll be able to use that flow chart. All right, let's start with an example. There's 3 for this section, I believe. Among 4 northwestern states, which are Washington has 51% of the total population, Oregon has 30%, Idaho has 11%, and Montana has 8%. A market researcher selects a sample of 1,000 subjects, with 450 in Washington, 340 in Oregon, 150 in Idaho, and 60 in Montana. Okay? At a 5% significance level, test the claim that the sample of 1,000 subjects has a distribution that agrees with the distribution of the state populations. All right, so the only conditions that we need to deal with is that the data is selected randomly. Safe to assume so, I would say. So let's start with the claim statement. We really need to know what we're talking about here. So if we can identify that claim statement, then we can proceed. Let's see. It says, test the claim. Okay, here we go. That the sample of 1,000 subjects has a distribution that agrees with the distribution of the state populations. Okay, so we're not sure where this market researcher selected a sample from, but we're trying to see if this sample has the same percentages as what it's believed to be, okay, which is stated in the first sentence. The 51%, 30, 11%, and 8%. All right, so let's go with the null hypothesis. Well, we're talking about a distribution, and this distribution has certain proportions. In this case, we'll call 1 Washington. Yeah, we'll call Washington 1. We'll call Oregon 2, Idaho 3, and Montana 4. So P1 would be, they told us what, 51%, 0.51. P2 is for Oregon, that's what, 30%. P3 is 11%, Idaho. And Montana has 8% of the population. The alternative is, if we can show that at least one of these proportions is different than what it's expected to be, then we can essentially reject this whole null hypothesis. Okay, even though maybe two of them are right on the money, if a couple of these are just off, right? Because one can't be off on its own. If one is off, then another one must be off at least. The claim is that we're talking about the entire distribution fits this model. Okay, so even though, again, a couple of these proportions could be right on the money, that doesn't mean that the distribution is accurate. All it takes is one proportion to be off. All right, so that's how we would say that. At least one of the proportions is different. I am underlining that word proportions because later on in another section we will talk about means. Step 2, our alpha is our significance level. Step 3, okay. So let's come up with the observed counts and the expected counts. That's our first order of business here. Again, from the data, really, that's where we come up with the observed values. We have in Washington, what was the observed here? It looks like there were 450 in Washington. Oregon, I believe there was 340. Idaho, 150. Montana, 60. Okay, this is where this whole expected values shows up. It's that one formula. That's your expected equals n times pi. Now, each one of these proportions is different, so that's why we have to use this formula. Otherwise, if they were all the same, then we would just use n over k and make it very easy for us. We do have a problem that's coming up in the next example that deals with that, but for now we are dealing with different proportions with different values. Okay, so for Washington, again, Washington is 1, so E1 would be equal to n times P1. Well, what's n? Remember, n is the total number of observations, really. That's what this is, okay? N is equal to the sum of your total observations. If you were to add these, we would get 1,000, okay? And they actually told us that, I believe, at the very top. Yeah, 1,000 subjects. So we have 1,000. And of these 1,000, how many were expected to come from Washington? Well, 51% of them, right? Times 0.51. 1,000 times 0.51 comes out to be 510. See how that works? If there's 51% of our population is from Washington, then out of 1,000 people, 51 times 1,000 is 510. And we're going to do that for each category. So E2 would be n times P2. And again, it's the same 1,000. P2 is up there, 30%. 30% of 1,000 is 300. Now, these numbers don't always come out to be nice whole numbers, and that's fine. I just chose an easy example that deals with nice whole numbers. We will deal with an example that gives you decimal values. Okay. E3 is n times P3, which again is 1,000 for your n. And up there is 11%. So that'll come out to be, well, what's 11% of 1,000? That's 110. All right, just move the decimal place. E4, again, that's n times P4, which is, our n is 1,000. Our P is 8%, so 0.08. And 8% of 1,000, that should just be 80. Okay, this is where you want to check to see if the sum of your expected values comes out to be your n, right? N should also come out to be the sum of the expected values. And if you add up 510 plus 300 plus 110 plus 80, you should also get 1,000. Okay, that's a nice way to check. Okay, so those counts, each list of these counts has to add up to the same total. Okay, again, this is your data, and this is essentially what we expect in the null hypothesis. So now we're going to go on to calculating the test stat. We're still in step 3. So we're going to calculate the test stat. And that test stat is the following formula. All right? It's a chi-squared, and it's the sum of a fraction. In the numerator, we have the observed count. That's an O minus E, that quantity squared divided by E. And we do that for each category. So there are 4 categories. So that means there's going to be 4 terms here. So just because I want to take advantage of the space here. All right. So we do it for each list here. So we're going to do parentheses squared over plus parentheses squared over plus, I might run out of room, parentheses squared plus parentheses squared over. Okay, each one of these terms corresponds to each one of these rows. Okay, so let me change up the color just so you can see. Okay, so what do we observed in Washington? Well, we observed 450. And what do we expect? Let me highlight these. These are the numbers I'm looking at. We expect 510, and the expected value down here is 510. Go on to the next row, 340 minus 300 over 300. Again, these quantities in the numerator are squared. Third row, 150 minus 110 divided by 110. And we have finally in our fourth term, fourth row, 60 minus 80 over 80. Okay, so in an ideal world, the observed counts would actually be exactly what we expect it to be. For example, that 450 should be 510, right? So if you were to actually subtract these two numbers, and there was 510 minus 510, then what would you get there? Wouldn't that be 0? And then 0 squared is just 0. So this whole term would be 0. And it would essentially contribute 0 to this sum. Okay? So the closer what we have the observed value match up with the expected value, the smaller our test stat should be. Okay? And on the chi-squared graph, which we'll draw in a little bit, the closer it would be to 0. Okay? The further these are away, and then when you square it, and then divide it by the expected value, the more that contributes to this test statistic. And the further away from 0 on the graph it becomes. Okay, so let me get an approximate answer for this. Now, I'm doing this just for demonstration purposes. I'm going to round to 3 decimal places for each term. But in reality, you should have more decimal places retained. In fact, in reality, I'm going to show you a better way to do this in your calculator that retains all the decimal places for you. If you were to run this through your calculator, you get 7.059 plus this term is 5.333 plus 14.545 plus 5. Okay, now let's just really examine these 4 numbers here. The smallest number that I see is the 5, which is the last one here. That one contributes less to the error, you see. The 60 and the 80 are closer to each other than all the other categories. Okay, so for Montana, 60 and 80 are closer to each other, just by the looks of it from those numbers. The ones that are the most off was that 14.545 in relation to each other. 150 and the 110 was more off than all the other ones. And so that contributes more to this error, to this test stat. Okay, let's add them all up now. This test stat comes out to be 31.937. Okay, that's our test stat. We're going to go ahead and draw this picture. All right, so it's a chi-square distribution. Starts at 0 and it goes off all the way to infinity. This test stat, this 31.937, it's hard to tell where it lies along this axis here, but typically your degrees of freedom are close to the peak. Our degrees of freedom in this case was what? 4 minus 1, which is 3. So that 3 would probably be somewhere around here, roughly. So it means 31 would be way out here. So I'm just going to erase that 3. Okay, and I just said that these are all right-tail tests. Okay, you notice that if what we observed and what we expected was exactly the same, then each one of these terms would have been 0. And our test stat would have been 0, so that would have brought this test stat all the way over here. And then the area to the right of that value, let's say it got down to like way over here, that area would have been really, really large, and we would not be able to reject the null hypothesis because we see that what we observed and what we expect is not different from each other. So why would we reject the null hypothesis? But in our case, it looks like it is going to be significantly different. We had to calculate this p-value here. That can be done in a number of ways. You can use Chi-squared CDF. I'm kind of showing you the long way right now. We have a lower, upper degrees of freedom. The lower would be this value, 31.939. Upper goes all the way to infinity, right? E99. Degrees of freedom is the categories minus 1. We had 4 categories, so 4 minus 1 is 3. And you can calculate that. And I get something like 5.39. Again, probabilities cannot be whole numbers, so this is definitely times 10 to the negative 7. So it's a really tiny value. Okay, so I do want to show you how to do this if you have a TI-84. Let's go ahead and do that. Let's switch over to the calculator really quick. Here we are on a clear home screen. And let's see, if I want to enter this data, then we have to go into the stat menu and go to edit. Okay. Now you could put your observed counts in L1, your expected counts in L2. If you're using the in calculator function, it doesn't really matter. You can put in any order. It's only when you're using that Math 200A program where the order matters. All right, I'm going to put my observed counts in L1. So I'm going to clear out this list. 450, 340, 150, 60. Okay. My expected counts are 510, 300, 110, 80. Okay. Now, if you have a TI-84, that's all you have to do, really, okay, as far as data inputs. Okay, I'll address an easy way to make that calculation in just a second. But let's go ahead and exit out of this. So second quit. If you go to stat, we're going to go to test. And if you actually go up and look for something called Chi-squared GOF test, there's actually a Chi-squared test and a Chi-squared GOF test. Make sure you choose the one that says Chi-squared GOF test. Okay. For those of you with the TI-83, again, you do not have this function in your calculator. So there'll be an alternative way to doing it. Essentially like what we just did right now, the Chi-squared CDF method that we previously did. But let's see if we can confirm the same answer here. Okay, so if you press enter on that, it's asking where is your observed list and where is your expected list. Again, you had the freedom to put them in anywhere, so just make sure you locate those correctly. My observed list was in L1. My expected list was in L2. My degrees of freedom was the number of categories, which we have 4, right? Because it's Washington, Oregon, Idaho, Montana. 4 minus 1, so that would be 3. And let's go ahead and calculate that. All right, you see the test stat there, that 31.937. I guess if we were to round that, 938 would be more accurate. Again, my version of it was because of demonstration purposes, right? We were rounding to 3 decimal places. And the p-value, oh, my p-value is pretty close. Yeah, it's actually right on the money. 5.39 times 10 to the negative 7. Okay, so that's how you would do that. Now again, for those who with the TI-83, well, first of all, what did he notice that I did here? Well, I didn't have to do any of that calculation for the test set. It did it for me, right? So if you have a TI-84, it calculates your test stat and your p-value. Okay, so those TI-83 owners, you might think this is very unfair, but there's a fast way to calculate the test stat also. Let me show you how to do that. Let me go ahead and quit out of this. If I go to, again, our edit page here. All right, so L1 and L2 are already listed here. If you go to L3, okay, and if you actually scroll up to where the L3 is actually highlighted and press enter, you can actually calculate a formula, okay? And this is what we're gonna do. We're gonna use the formula of our test stat, which is the observed minus the expected quantity squared divided by the expected. Okay, so we need a parentheses. And the observed list is L1, so you want to press second 1 and then subtract off the expected list. Second 2, parentheses. We're going to go ahead and square that. There's the square button. And divided by the expected list. Second 2. All right. That should automatically generate each one of these values. Let me press enter. Yep. And that's exactly what we have. Let me just scroll over to the right here to show you what I have there. You see that? You have the 7.0588, that's there, 0.059, 5.333, 14.545, and then 5. You see those 4 terms are exactly those. And if you were to add those up, you'd get the 31.937. Okay. What you can do here is if you just exit out of here, that's an L3, remember that. Go to Stat, Calc, 1-bar Stats, L3, and if you just want to add those up without having to do it by hand, just look at that addition, that sum of x. You see how the 31.937, yeah, that's how you would actually do that. So there's a couple ways to do it. So those of you with the TI-83, yeah, you're limited a little bit, but I just showed you a couple ways to use your technology to your advantage. Okay. So those were all the ways to calculate your test stat and your p-value. I gave you a bunch of different options there. So now we're going to compare the p-value and the alpha here. Again, our p-value and our significance level are, well, your p-value is 5.39 times 10 to the negative 7. Significance level was from step 2, which is just 5%. And your p-value is definitely less than your significance level. So, again, what does a p-value represent? Well, it represents the probability of making a type 1 error. What's a type 1 error? A type 1 error is an error in such that we reject the null hypothesis when it was actually true. Okay, we don't want to make that error. All right, we're only willing to make that error up to a 5% chance of making that error. The fact that we have a very, very low chance of making an error, we're okay with rejecting the null hypothesis because we'll take that chance. It's very small. Okay. And then step 6, we're going to use that conclusion statement. Now, one thing I didn't do was identify the claim statement, right? If we read the claim statement, it says a sample of 1,000 subjects has a distribution that agrees with the distribution of the state populations. So yeah, that was the claim, that it agrees with this distribution. In step 5, we found that we had enough evidence to reject the null hypothesis. So we would say there is significant sample evidence to reject the claim that the 1,000 subjects have a distribution that agrees with the distribution of the state populations. Okay, so let's look that up in the flowchart. Okay, we're here at the flowchart. The claim was the null hypothesis, so we're going to go this direction. Were we able to reject it? Yep. So there, we say that there is sufficient evidence to warrant rejection of the claim that, and then we just restate that original claim statement. And that is that the sample distribution agrees with the state population. All right, example 2. If we have the results of 600 rolls of a die, does this set of counts differ significantly from the expected 100 per category? That is, we want to test the hypothesis that the die is a fair one. Okay, so for a die to be fair, that means the probability of each side occurring has to all be the same. So let's go ahead and highlight that claim statement, that the die is a fair one. The die is fair. So that's basically the claim statement in a nutshell. All right, let's start with the hypothesis statements here. And since we're talking about a distribution here of all the sides of a die, you can see that P1 and each side has the same probability. So P1 equals P2, which is equal to P3, which is equal to P4, P5, P6, right? There's 6 sides, that's why there's a proportion for each one of them. And they're all equal to the same value, which is 1 in 6. In the alternative, all we have to say is that at least one of the proportions is different. Now, which one of these statements lines up with the claim statement? For a die to be fair one, that means the proportion for each side has to be 1/6, right? So that's what that means. So it should be the null hypothesis in this case. Yeah, that's a complete step 1. Step 2 is our significance level, which I believe they tell us it's 5%. That's a typical value. Step 3, let's go ahead and write that down below here. Now step 3 is calculating the test stat. In order to calculate the test stat, we need to have our observed counts and our expected counts, or frequencies. Okay, so this is the result of rolling 600 die, right? If you were to add up these observed counts, this is n equals 600. And again, we should expect 100 from each side of the die if it was a fair die, right? But of course, in practice, you actually do this. Sometimes you get, in this case, you got 90 for the first phase, 105 for the second phase, 115. Now, they're not, I mean, the one that deviates the most from what's expected is phase 3, which is 115. It's 15 units away. But we're trying to see if any one of these phases deviates so much that we can conclude that this die is not a fair die. Okay. So again, what's the expected value here? Since we have all the same sides, E1 would just be essentially n over k, which is 600 over 6, which is the number of categories, right? You can also use this formula here. That would be 600, and what would be p? Well, that's 1 in 6, right, from over here. 600 times 1 in 6 is the same thing as 100, right? So either way, you'll get 100, okay? And of course, E2, E3, E4, E5 are all the same because the same n and the same k, so you get 100 for each one. And again, the sum here has to be the same as our observed counts, right? Okay, so the total expected counts and the total observed counts have to add up to be the same total, right? Which in this case is 1,000 rolls of the die. All right, so in step 3, we're going to calculate our test stat. Now, of course, I've already shown you how to do this in your calculators here. Many different ways, but I'm going to continue to do it the way the TI-84 does it, okay, using the Chisquared GOF test. Okay, for those of you at the TI-83, just refer to the previous example on how to calculate the test stat in a very easy way, and also how to calculate the p-value using the Chisquared CDF. Okay, so remember that. Test stat. Is a chi-squared, which is the sum of your observed values minus your expected values squared over the expected value. Okay. Now what we're going to do here is we're going to call one of these lists L1 and one of them L2. Now it doesn't really matter which one you call L1, L2. For those of you using the Math 200A, you would have to call observed L2 and expected L1, but if you're using the function in your calculator, you don't have to really be worried about that. But just for fun, I'm going to call this one L2, this one L1, and I'll put that in my calculator in that order. Okay, so let's go to the calculator. Okay, if I go to Stat, Edit, I'll go ahead and clear out all these. Okay, I said I was going to put my expected under L1, so it's going to be 100 all the way down. Okay, there's 6 of those. And the observed counts are 90, 105, 115, 95, 95 again, and 100. So yeah, the side with the 6 actually was right on the money. It was exactly 100. So that's not going to contribute anything to this test stat. Okay. The one that will contribute the most, I believe, is phase 3, just because 115 is much more different than 100, but probably not significantly different. Again, our test stat and p-value will help us determine that. All right, let's go ahead and exit out of this. So second quit. And let's go to stat. And if you have the function in your calculator, if you have a TI-84, you're going to have chi-squared GOF test. Again, if you have a TI-83, just do it the way that we did in the previous example. Okay. Now, my observed were actually in L2, so I'm going to reverse this. This is L2, and this is L1. Okay. Why did I do that? Just for fun, really. Also, one of the main reasons I'm doing that is just if you do happen to be using the Math 200A program, then it requires this order. All right. What's the degrees of freedom? Well, how many categories were there? Well, there's 6 faces, right? So it's categories minus 1. So 6 minus 1 is 5. So make sure that you put a 5 there. And then let's go ahead and calculate. All right. Our test out actually just came out to be exactly 4. That's kind of odd, but it just happened to be that way. I think just the numbers worked out that way. And then the p-value, okay. So this is a 54.9% chance that we're wrong if we reject the null hypothesis. So that's a pretty high chance. We don't want to take that chance, so we're not going to reject the null hypothesis. All right, so let's go to step 3. Our test stat was 4. I use GOF test, chi-squared GOF test. Again, you can also use that Math 200A in your calculator. That would be an external program. Or using chi-square CDF to get the p-value. That's a complete step 3. Part of step 3 is also this table, coming up with this table correctly. That's part of step 3. Step 4 is drawing a graph. We're going to need a p-value. And from that output, the p-value here was, what was that? If I just round to 3 decimal places, 0.549 from the calculator. We're dealing with the chi-square distribution skewed to the right, because of this thing. So our graph has to match up with our test stat. Goes on forever, starts at 0, goes on to infinity. Now about the 50% mark is typically around somewhere around here. And these are all right tail tests. So this 549 business, I would say it's probably test stat to represent about 50% to the right, 55% to the right would be probably somewhere around there. Just kind of eyeballing it as much as I can. And that test stat is 4. Okay. So that is a, and the area of the shaded region is your p-value there. Step 5 is that we make our decision. Decision is made by comparing your p-value to your significance level. Again, the p-value is 0.549. Significance level, I believe, was what? 0.05. And that's definitely greater. So we're going to fail to reject the null hypothesis. And the conclusion statement is, well, we failed to reject the null hypothesis. So in a sense, we say that the null hypothesis is still true. Okay? And if that's still true, that's our claim, right? We said that it's a fair die. So there's not sufficient evidence to reject the claim that the die is fair. That's essentially the wording there, more or less. Let's go to that flow chart to get the precise wording. Okay, so the null hypothesis was the claim, so we go in this direction. Were we able to reject the null hypothesis? No. Okay, so the wording here is, there is not sufficient evidence to warrant rejection of the claim that, and I believe the claim was that the die is a fair one. Okay, let's go ahead and write that. Okay, let's do another one. Last example of this section. It says a supervisor at Fast Track Professional Temporary Services Incorporated suspects that her employees are more likely to call in sick on Mondays and Fridays than the other days of the week. To test this claim, she collects data on the number of people who call in sick on each day of the week. Her data are summarized in the following table. Okay, so what we have here is a supervisor suspects that her employees call in sick more on Mondays and Fridays. Well, there looks to be some sort of uptake on Friday there, right? And well, somewhat of an uptake on Monday. Probably more on Thursday than Monday, but she suspects that on Mondays and Fridays there's more of an uptake in people calling in sick. And maybe the reasons for that is people probably aren't sick and they're just taking Fridays and Mondays off because they're trying to make a 3-day weekend out of it, right? So maybe she collected this data over a month. It doesn't really say, but it doesn't matter, okay? So she wants to test this claim. So we're trying to test the claim that essentially people should be sick on every day of the week in equal amounts, right? There shouldn't be one day that people happen to be sick more than others, right? So we expect the number of sick people to be the same for each day, okay? So that's what they're saying here. Okay, so down below it says, test the claim that the relative frequencies of days in which employees call in sick is not equal for the 5 days she works. Okay, the relative frequencies. That's essentially the proportions, right? Okay, let's go ahead and start with our hypothesis statement here. Okay, so we suspect that they all are the same at first until there's evidence to provide that they are not. Okay, so we have to say that, I guess we can call Monday 1, Tuesday 2, and so forth. So P1 is equal to P2, which is equal to P3, which is equal to P4, which is equal to P5. All right, so these 5 days, right, there's 5 work days, and if each one has the same probability of occurring, and we know that all 5 probabilities have to add up to be 100% or 1, then what does each one of these proportions have to equal? Well, doesn't each one have to be equal to 1 over 5, right? 1/5, 1/5, 1/5, 1/5, 1/5, right? That way it all adds up to just 1. Okay, make sure that that makes sense, okay? And all we have to do is say that at least one of these proportions is different to prove that the null hypothesis is not right. That's all it takes. Now, what does our claim statement, the highlighted sentence, line up with? The null hypothesis or the alternative? Well, let's read that again. The relative frequency of days in which employees call in sick is not equal for the 5 days. So she actually suspects that it's not the null hypothesis, that they're not equal. She suspects that it's the alternative, that at least one of these is different, right? In particular, she believes that Mondays and Fridays have a higher frequency of people calling in sick. Okay, let's see if she's right. Right. All right, so step 2 is our significance level, which I believe they say is, yeah, right there, 5%. Step 3 is really coming up with these expected counts and then calculating the test stat. So the expected counts are part of that. All right, so we're going to come up with our test stat here. And to find the expected counts here, well, it's going to be, for E1, it's going to be n times P1. Well, what's n? Well, n has to be the total number of observations. So we have to calculate that over here. The total number of observations. All right, if I calculate 9 plus 7 plus 7 plus 11 plus 13, I get n equals 47. So we have 47. And then P1 is just, well, they're all the same. It's 1/5. Okay. 47 times 1/5, or 47 divided by 5. If I calculate that, I get something like 9.4. Okay. And since this calculation is going to be the exact same n and p for each day, then it's going to be 9.4 all across the board. Okay, what are we saying here? What's the interpretation here? It says, on average, if every employee calls in sick randomly, then we should expect each day to have the same amount of sick people calling in. And if there was 47 people that called in sick, that evenly spreads across all 5 days as 9.4, 9.4, 9.4, 9.4, 9.4. Does that make sense? Okay. Again, if you were to add up 9.4 5 times, you would also get 47. So these two sums have to add up to be the same. All right, let's go ahead and let's put this under L2, L1, and let's go ahead and run Chisquared GOF test. Let's go to the calculator for that. Okay, we're on a blank screen on our calculator here. Let's go to Stat. Let's go to Edit. Let's go ahead and clear out these lists. And L1, I'm going to put my expected frequencies. I'm going to put the 9.4 all the way down 5 times. And L2, I'm going to make that my observed counts. So we have 9. Okay, double check those inputs are correct. Okay. Now let's go ahead and jump out of this. Second quit. Let's go to Stat. We're going to go to Test. If you go upwards until we find Chisquared GOF, that's the one we want. My observed are in L2. My expected are in L1. What's my degrees of freedom? Well, it's always the number of categories minus 1. How many categories do we have? Well, there's 5 days, right? So it'll be 5 minus 1, which is 4. Degrees of freedom are 4. And let's go ahead and calculate that. All right. My test set is a 2.8936. But my p-value it's pretty large, right? We're not going to be able to reject the null hypothesis. Just by looking at those numbers, we expected 9.4 people to be calling in sick each day. The one that deviates the most from that is on Friday, which is 13, and apparently that's not enough of a deviation for us to completely say that people are calling in sick more often on Fridays or any one of these days than other days. Okay, essentially like Tuesday and Wednesday are close enough to the 9.4, and Monday is also close enough to 9.4 to say that it doesn't deviate that much from what's expected. All right, so the test stat here is 2.89. All right, again, we use Chisquared GOF test. Step 4 is drawing a picture. We need a p-value from that output. I believe it was if I'm rounding to 3 decimal places, it was 0.576. What kind of graph do I use? Well, it's chi-squared, so we're going to have to use a skew to the right type of graph. It starts from 0, peaks somewhere. The peak is usually around the number of degrees of freedom. So in our case, degrees of freedom was like, what was it, 3? No, 4. So the peak is somewhere around there. Our test stat of 2.89 is around there too. So, and the area to the right of it, again, these are always right tail tests, represents 57.6%. All right, that's that area. Okay, so we're not going to reject the null hypothesis. Okay, so that means we don't have enough evidence to support our claim. Okay. So step 5, decision. Compare our b-value to our significance level, the p-value being 0.576, significance level being 0.05. This is definitely greater than, so we fail to reject the null hypothesis. Step 6, we're going to come up with our conclusion statement. Again, We failed to reject the null hypothesis, so in a sense, the null hypothesis is still true. If the null hypothesis is still true, then that means we're not able to support our claim. Okay, so let's go ahead and go to the flow chart for that specific wording. Okay, we're here at the flow chart. The claim in this case was the alternative. Were we able to reject the null hypothesis? Nope. So we say that there is not sufficient sample evidence to support the claim that, and then we restate the original claim. And what was the original claim statement? Well, it was that the relative frequency of days in which employees call in sick is not equal for the 5 days. Okay, you can kind of paraphrase that a little bit. I'll just replace the word relative frequency with proportion. Okay, that's it for this section. Thanks for watching.